Some of this is review. In Science 10, you learned that speed is the distance traveled in a given unit of time. As an equation, you learn this. We use v for speed, velocity, equals distance over time. Average speed is total distance divided by time. Oh, let's try that again without looking like I'm crossing it out. Average speed is total distance divided by time, and instantaneous speed is the speed of an object at a particular instant. We'll talk about the difference as this progresses. If an object moves along at the same speed over an extended period of time, we say that its speed is uniform or constant. We say that it's moving at a constant speed or a uniform speed. If you're on the freeway and there's no traffic and you're doing 100 kilometers per hour and you do that from Chilliwack to Vancouver, we would say you're traveling at a constant speed. Now, that doesn't really happen because, Sean, that you're never on the freeway without any traffic, even at 2 in the morning, so you're occasionally having to hit the brakes or speed up. Really, most of the time when we talk about speed for driving, that's an average speed. Certainly when you're city driving, it's an average speed because there's lights. You're stopping, you're speeding up, you're stopping, you're speeding up. Uniform speed is uncommon, but it's possible to achieve nearly uniform speed in some situations. For example, a car with cruise control can maintain a fairly constant speed on the highway as long as traffic is good. Certainly for stretches, you can do it. Usually, however, a vehicle is making small changes in speed and direction all the time. If an object is not traveling in a straight line all the time, then its direction becomes important and must be specified. When both the magnitude and the direction of a speed are specified, we call the two properties, speed and direction, the velocity of an object. So if you say that your car is moving at 80 kilometers per hour, you've just told me the speed. If you say your car is moving at 80 kilometers per hour due north, now you've given me the velocity. Velocity is a vector, and all vectors have magnitude and direction. And that's going to become important this year, and especially in Physics 12. So the difference between speed and velocity becomes important in situations where direction changes during a trip. For example, if I throw a ball into the air, like this, on the way up, it's traveling upwards. On the way down, it's traveling downwards. So both its speed and its direction are changing throughout its trajectory. Therefore, we would want to be talking about the velocity in that situation because you want to know whether it's going up or going down. And probably an easy thing for us to do, Matt, would be to say going up is positive, going down is negative. It works for the most part. Then we have the fun stuff, acceleration. Whenever the velocity of an object changes, the object experiences acceleration. Acceleration is defined as follows. It's the change in velocity divided by the change in time. It's the change in velocity divided by the change in time. The symbol that we use for acceleration is capital letter A. Sorry, lowercase letter a, not a capital letter A. But I should put a vector symbol above it as well because acceleration is also a vector. It has direction. Does anybody remember from Science 10, what was the symbol for a vector? It used to be a complete arrow like that to show it has direction, but over the years we've gotten lazy and we just draw the top half of the arrow because you can do that in one pencil stroke, and we clue in, it's supposed to be an arrow. Mr. Dewick, if we forget to put the symbol, will you take marks? No, probably not. I'm more concerned with your final answer, and we'll talk about that as we get there. So velocity has the same symbol as speed, which is v, except velocity would have, that's a velocity, that's a speed. We're going to use some symbols. We're going to use, because if we have a change in velocity, we're going to talk about the velocity at the start of the time interval, and we're going to call it either v0 for velocity at time 0, or we'll sometimes call it vi for v initial. I prefer vi, but I know a lot of textbooks use v0. Okay. If you're British, you don't say v0, you call that v0. And I had a British physics teacher, so you may occasionally hear me call it v0 without thinking about it at all. And we're going to call the velocity at the end of the time interval vf. What do you think the f stands for? Final. Final and initial, or final and 0. Then the change in velocity will be that, final minus initial, because change in anything is final minus initial, final minus beginning. If the time at the beginning of the time interval is time 0, and the time at the end of the time interval is time final, then the change in time is that. So using symbols, I can now give you an equation for acceleration. Hakeem, I can tell you that acceleration is the change in velocity, final minus initial, don't want to muck it up, over the change in time. Or the symbol for change in terra that we use is a triangle, although in science we call it a delta because it's a Greek letter. We say it's delta V over delta T. You may have occasionally been watching some kind of a sci-fi movie or something like that, and you may have even heard some expression where you don't have enough delta V. They're saying, you need to speed up. Or slow down, probably, but usually it's speed up. Okay? Where the triangle symbol is shorthand for change in, or interval. Little note, change in anything is always final minus initial. Sean, what's change in anything? Final. Nathan, what's change in anything? Sam, what's change in anything? Worth having, especially in Physics 12, because in Physics 12, I'll ask you, for example, to find the change in voltage. And every year I have kids that freeze up. I don't know what the change in voltage is. Why don't you find the final voltage, find the initial voltage, and then subtract them? Or I'll ask you to find the change in magnetic field. I don't know what to do. Why don't you find the final magnetic field, find the initial magnetic field, and then, Jordan, just subtract them. So I really hammer that in Physics 12, but we'll try and flog it to death this year too. All right. Since velocity has two aspects to it, flip it over, the phone. Front row, not the best place to try and cheat. There you go. Since velocity has two aspects to it, speed and direction, acceleration can occur two ways. If speed changes, or if direction changes, or if both speed and direction change. In this unit, we'll mostly be looking at situation A. Physics 12, we'll look at all three. Let me give you an example. A runner is racing in a 100-meter dash, and he accelerates from rest. Underline the word from rest. That's going to the phrase from rest. That's going to be really important. That's an important physics phrase that I look for, Riley. To a speed of 9 meters per second in 4.5 seconds. What was his average acceleration during this time interval? I have an approach in physics, and my approach in physics, if you go back to the previous page right here, you got some room. I have a little acronym, and the acronym is DFIC. Connor, when in doubt, DFIC. If you don't know what to do, you're going to hear me say, Mr. Dewick, how do I do this? Have you tried DFICing? What does DFIC mean? It's an acronym. It's a procedure. Tanisha, it means this. The D stands for list your data. Hey, write down everything the question told you. The F stands for find a formula that has that data and what you're looking for in it. The I stands for insert the data, the numbers. And the C stands for calculate your answers. That's going to be one of my little problem-solving strategies all year long. DFIC. The other one that I have is DULP. Okay? DFIC and DULP. And DULP stands for, when in doubt, draw a little picture. We're going to be doing that an awful lot as this unit progresses. You're going to hear me say, what's going on? We better DULP. Draw a little picture. So here, example 1. First thing I'm going to do is I'm going to start listing the data, what they gave me. And I can figure out what's what by looking at the units. In this course, Zach, it's really going to be worth it if you memorize what units go with which values. If you do that, it becomes almost like connecting the dots, filling in the blanks, as opposed to heavy, heavy thinking. I'll show you what I mean. The first number I see is 100. But I'm looking at the units next to the 100. What are the units next to the number 100? That's a distance. I may use that, I may not. I also see a 9.0. What are the units next to the 9.0? Meters per second. Hey, what's that? That's a velocity. Final or initial? How'd you figure that out?
The initial is from that.
So I'm going to write this. V final is 9. I don't care if you don't put the 0.0 in your list in your data. And I don't even care if you don't put the units in your list in your data. You can, Curtis, if you want to. I sometimes do if it's really, really complicated. I sometimes don't. Honestly, it depends on how much room I have to write. So, Amanda, what did you tell me the initial velocity was?
From last week,
0. I see another number there, 4.5. 4.5 what? What is that? And then I always ask, hey, what are they asking me to find? What are they asking me to find? A equals question mark? Turns out I don't need this displacement. And I also, he's not running the full 100 meters, so that was a bit of a trick, a bit of a sneaky extra information that you don't use. I'm looking for an equation that has an A, a V final, a V initial, and a time in it. Now, going back to here for a second, you don't need to go back to here. This is our equation, except time is always a change in, and so if you want to go back to here, we get lazy. We often go change in velocity over time. Time is always a delta, and so over the years, Riley, we've stopped writing the delta because it's, oh, for Pete's sakes, it's a delta there. It's the one that's always a change in, because to measure time, aren't you always having to start and stop a stopwatch? There's always a final minus initial. So it's change in velocity over time. In fact, it's V final minus V initial over time. As an equation over here, acceleration equals V final minus V initial over time. DFIC, we've done the D, we've listed our data. We've done the F, we found a formula that has final velocity, initial velocity, time, and what we're looking for. And conveniently, Perry, what we're looking for is already by itself. That won't always be the case. We will get very good at rearranging formulas in our head on the fly. I'm going to push you all to master that skill because it's a huge time saver, it's a huge way to cut down on your mistakes, and it's nerdily cool. Let's plug in the numbers. Insert 9 minus 0 all over 4.5. I made these numbers up so they work out nice. I can probably do this in my head, 9 minus 0, but if I couldn't, I would remember how many numbers are there on the top here. 2, I would have to go bracket 9 minus 0, close bracket, divided by 4.5. Now, I probably wouldn't bother typing the 9 minus 0 because, well, I can go 9 minus 0 in my head, Dylan, pretty easily. What is 9 minus 0? In fact, I would even argue I can go 9 divided by 4.5 in my head. What's 9 divided by 4.5? Yeah, I cooked the numbers. Oh, hang on. How many sig figs? 2. How many sig figs? We're dividing. How many sig figs should I put in my final answer? So I'm going to go 2.0. Oh, but in the same color ink, Mr. Duke. Units. Well, acceleration is measured in, well, what's velocity measured in? Meters per second in physics. And then that's divided by time. Acceleration is measured in meters per second per second. But we simplify that. We tidy it up. Instead of saying meters per second, does anybody remember what we measure acceleration in? It's meters per second squared. This is really 2.0 meters per second squared, and that's your next unit that's worth memorizing. If you see a meters per second squared, I'm telling you it's an acceleration. It is. So the standard unit for expressing let's try that again. A standard unit for expressing acceleration is meters per second squared. What that's saying is if an object is accelerating at 1 meters per second squared, it's increasing at a rate of 1 meter per second each second. So let's suppose I'm doing 20 kilometers per hour, 20, and I'm accelerating at 5 meters per second squared. After 1 second, I'm doing 25. After 2 seconds, now I'm doing 30. After 3 seconds, now I'm doing 35. After 4 seconds, now I'm doing 40. Okay. Number 2. A UFO is reported as accelerating from rest to 680 kilometers per hour in a time of 2 seconds. What's its acceleration? Okay. DFIC. 680. What's that? Look at the units. Oh, it's which velocity, final or initial?
Final.
And since this is weird units, this time I am going to write them out. What else do I know? Oh, 2.0, what's that? Time? What do they want me to find? Acceleration, all right, A equals question mark. That's not enough, I need one more thing. There is something else they told me. What, AJ? Oh, once again, from rest, VI is 0. Have I got an equation that has V final, VI, A, and T in it? I do. It looks like this. Acceleration equals V final minus V initial all over T, which is going to be 680 minus 0 all over 2. Now this is going to be kind of a weird acceleration. This is going to give me, hey, what is 680 divided by 2? 340, and this is 2 sig figs, 2 sig figs, 340, the 0, 2 sig figs, so I can go with that. So I'm going to go 340, and this is kilometers per hour per second, because the 2 is in seconds. Elijah, that's kind of a weird acceleration unit. It is distance divided by 2 times, so it is distance divided by time squared. So the speed of the UFO is increasing at 340 kilometers per hour each second. You could write this acceleration as 3.4 times 10 to the 2 kilometers per hour per second. Although kilometers per hour per second is not the officially accepted unit for acceleration, it's often used when describing the acceleration of an automobile. Why? Because what do speedometers show on an automobile? Meters per second? Kilometers per hour. But when you're timing, what are you probably timing in? Hours? Seconds. I'm not a big fan of that unit myself. Okay. Homework to start out. 1, 2, 3, 4. Yeah, it's going to be all of them. 5, 6. And hang on, I may have some more here. So continuing on, doing 2 lessons in one day. Lesson 3, distance and displacement. In physics, my friends, every quantity in physics is either a scalar or a vector. Scalars have magnitude only. They have size. For example, mass is a scalar. Kilograms does not have direction. You can't say, hey, that's 80 kilograms north. Doesn't even make sense. Time is a scalar. Oh. Speed is a scalar. Vectors have both magnitude and direction. Vectors have both magnitude, and direction, so they have a size, but it also matters which way they're pointing. Force is a great example. So Jordan and Matt, stand up. And I'll have Connor, can you stand up as well, please, my friend? Matt, stand right here. Actually, Connor, stand right here. Matt, right there. Jordan, right there. Okay? Force is a vector. Connor's going to stand in the middle. Put your hands right here. Put your hands right here. Both hands, both hands, both hands. Face them. Both you push. They're canceling out. The net force right now is 0 because force, the direction matters. The fact that they're pushing against each other actually means that the directions are canceling each other out. If I compared that with, stop. Jordan, go around to this side. Okay, Matt, no, all the way around, all the way around. Matt, hands here, and Jordan, hands here. Heave him! Push! Okay. Now, suddenly he's accelerating. So force is a great example of a vector. Thanks. I just wanted to pick on Connor. Classic scalars. Time, mass, speed, and distance. Classic vectors. Force, which comes a couple units from now. Acceleration, it matters whether you're accelerating forwards or backwards, or up or down. What's the vector equivalent of speed? Velocity. Who remembers from Science 10, what's the vector equivalent of distance? Displacement. Nice. Vectors in a textbook are normally written in bold font. So the fact that that's been bold fonted, I know those are vectors, but that's very hard to handwrite. That's speed. That's a dumb way to do it. So we write an arrow above a vector to show that it has direction. But as I mentioned earlier, we've gotten lazy over the years, and so we often just write half the arrow. Chunk, chunk. One little stroke. Distance versus displacement. Distance is how far an object has traveled. Distance is how far an object has traveled. Symbol. Sometimes they'll use an X if they're talking about a graph and they want you to walk along the X-axis. or I usually use a lowercase d, which technically is bad physics, but it's easy to remember. In calculus, the letter D has a very significant special meaning, and so in first-year university physics, you'll almost always use either X or the letter S for distance. Why S? Latin. Displacement. Displacement is an object's change in position. Symbol, vector, or vector. Okay. Example 1, a bug walks along the number line right there. It starts at location A, gotcha, walks to B, gotcha, then turns around and walks all the way to C. What distance did the bug walk? Well, the distance is this path here. Yoink, yoink. How far it walked. How far did it walk grand total? Well, it went 4 to the right. And then how far did it walk to the left from the 4 to the right to get way over there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total distance, 14 meters. What's the bug's change in position or displacement? Well, where did it start out at, Jake? Where did it end up at? Which is what number? The displacement is negative 6.0 meters. What's the negative telling you based on this number line? To the left. So that contains the direction. Or you could say 6.0 meters left. The 6 is the magnitude. The negative, or the left, is the vector, is the direction. So the track out in the backfield, no, there's no more track there anymore, is there? Okay. If you're running around a track, your distance may be 400 meters, but if you end up back where you started from, what's your displacement? 0. Okay. Speed versus velocity. Average speed, we said was, oh, let's try that again, Mr. Duke. Distance over time. Technically, distance over change in time, where that delta means change in. Oh, as an equation, we have this. V equals d over t. We drop the delta for time because we know it's always a delta. What would the units be? Well, what do I measure distance in? Meters. What do I measure time in? So what would the units be? Meters per second. Speed, scalar or vector? Average velocity. Okay. Average velocity is displacement over change in time, where the delta means change in. As an equation, velocity equals displacement over time. Still meters per second units, but this is a vector. Is that okay, Elijah? Sorry? Displacement is d vector sign, yeah. So, if the bug's trip mentioned in example 1 took 2 hours, what's the bug's average speed in meters per second? Okay, the first thing that we need to do is we need to change this 2 hours to seconds. T equals 2 hours times, okay, I want hours to cancel, I want minutes on the top. 60 minutes is 1 hour. I want minutes to cancel. I want seconds on the top. 60 seconds is 1 minute. Okay. How many seconds was this bug traveling for? $7,200? Okay. What do they want me to find in A? So average speed, I said, was distance over time. We've got the, we have the time. What was the distance? What did we say in A? How far did he travel? 14? So 14 divided by 7,200. It's a bug. It's going to be a small number. I get 0.0019444444, and I think that repeats. Yeah? No? Sig figs, 2 sig figs, 2 sig figs. Let's go 2 sig figs. I'm going to go like this. 1.9 times 10 to the negative what? 1, 2, 3. Units? Meters per second. Oh, let's try that again, Mr. You look a little neater. Meters per second. What's the bug's average velocity? Okay. It's going to be displacement over time. It's still going to be a time of 7,200. But what was the displacement? Was it 6? Ah, negative 6? So we're going to get negative 6 over what's the negative telling us, Zach? Direction. Which way? And I get an answer on my calculator in scientific notation already. Negative 8.3 times 10 to the negative 4. Meters per second. Okay. Yep. But I think actually if I look up here, because this data was all to 2 sig figs, I think I can get away with 2 sig figs. I wrote down in my DFIC 1 sig fig, but I remembered, I'm pretty sure it was 6.0 when we did the math. Good argument. The real answer is I probably wouldn't be too fussy, but I prefer to go to 2 or 3 whenever possible, if I can. Jason has given Peter a football play to run. Any of you read Foxtrot comics? I love Foxtrot comics. The guy who writes them actually has his physics degree, and while he was in university, he also did a lot of doodling, and some of his friends said, hey, these are funny. You should publish some of these. So he does. The youngest boy, Jason, is an uber mega nerd, an uber geek, which I like, and the math and the physics that he throws in here is correct. So Jason's giving his older brother, Peter, a football play to run. Okay, here's the play. Go 40 yards downfield, then turn left and go 20 yards, then turn right and go 25 yards, then turn right again and go 30 yards, then turn right and go 30 yards, then turn left and go 10 yards, then turn left and go 15 yards, then turn left and go 20 yards, then turn left and go 50 yards, and I'll hit you with the ball. Peter thinks for a moment. Won't I be right back where I started? I can't throw very far. Peter says, okay, here's the new play, and Jason says, I never get to be quarterback. What distance will Peter run in order to complete this play? Well, the distance is going to be 40 yards downfield plus 20 yards plus 25 yards plus 30 yards plus 30 yards plus 10 yards plus 15 yards plus 20 yards plus 50 yards. Did I miss any? 40, 20, 25, 30, 30, 10, 15, 20, 50. Yeah. What's the distance he's going to run? Because we don't care about direction for distance. Someone add them up. Don't all rush for your calculators at once or anything.
240.
Sorry?
240.
Anyone double check? 'Cause that's a lot of typing. 240 once, 240 twice. One more. Give me a third confirmation from somebody. Yeah? 240 yards, because it's an American comic. Oh, B is considerably easier. What's his displacement? Zach? By the way, 0, if you write 0 instead of 0.0 or 0.00, I'm not fussy on sig figs for the number 0. What you're saying is, hey, I know there's nothing. The answer is nothing. It's actually 0.00000, as many sig figs as you really need me to go. It's not, answer is 0. Just like when we said VI was 0, we didn't even take that into account for sig figs. It's 0 point as many zeros as you need to match the number of sig figs that you need. What's your homework? So 1 to 6, and I got a bit more. So here's homework part 2. Have a little sheet for you. It says, below is a map of a happy country that lies deep within the subconscious of crazy physicists. When we feel stressed out or sad, we go to this country and we ponder kinematics problems as we travel from one happy town to the next. It makes us happy, and it will make you happy too. It's happy, happy. What I have here is a bunch of towns, and I've given you the distances in kilometers that the curvy roads are. I made them up. I didn't actually crunch the numbers, but the numbers are reasonably accurate. And then I told you on this map, scale 1 centimeters equals 10 kilometers. And this is where you're going to have to use your ruler. So on the back page, it says for each of the following, find the distance traveled in kilometers. So the distance is going to be the road lengths. So number 1 says from Fizzlestein to Rasmussen, through, you know what, from F to R through Q and S. If I go back here, so I want to go, don't write on your sheet, but I'm going to, from F to R through Q, and I want to follow that road. Distance is how far I've traveled on the road. Well, from F to Q, I've traveled 75 kilometers plus. From Q to S is 27 kilometers plus. From S to R is 104 kilometers. That's my distance, 75 plus 27 plus 104. What's my displacement? Displacement just cares about where I started from and where I ended up, and that's where you're going to need a ruler. What you're going to do is you're going to take your ruler, lay it down, and measure in centimeters from here to here. Now, mine says, that's inches. On my big screen, it comes out as like 47 centimeters, but that's because I've magnified the image. All of you have the same size image. Measure it, and what's 1 centimeter worth? What does it say on the scale on the front of the page? 10 kilometers. So if you get, and I'm making this up, Jordan, 7.6 centimeters, what you're really saying is it's 76 kilometers. Okay, that's your displacement. Is that all right? Make sense? So number 1 wants you to find distance. That's going to be the road lengths. Add them up. Displacement. That's going to be your ruler length times by 10. Average speed. That's going to be distance divided by the amount of time the question told you it takes. Average velocity. That's going to be displacement divided by the amount of time. And here I am going in kilometers per hour, and I'm pretty sure on the back of the sheet every time that I give you is in, it's in hours. Does that make sense? Yeah, so you got two things, 1 to 6 from the previous lesson, and this. You can finish them all in class pretty easily.